In this video, we are going to discuss a property of objects called moment of inertia. And this property is going to be the analog of mass for rotational motion. So to begin, let's just do a quick review of what mass actually is. We've gotten really good at visually identifying when an object has more or less mass, but what does having more mass actually mean beyond just it has more stuff in it? Let's look at two lab carts that are being pushed by the same 10 Newton force. One cart has a small amount of mass and the other one has a large amount of mass because we've placed a couple of these metal bar masses on top. Take a moment and just predict how these carts are going to move compared to each other once I set this animation into motion. Will they move in the same way or will they move in different ways? As we can see, both carts accelerated because they were both experiencing an unbalanced net force, but the way they accelerated were a little bit different, and that was caused by the mass. This less massive cart was less resistant to acceleration, or it was easier to accelerate, but it didn't resist it as much. But the car with more mass was more resistant to acceleration. It was harder to get this larger cart to speed up. And that's really what mass is. When you have more mass, you have more inertia because mass is a measure of an object's inertia. And inertia is a measure of how resistant an object is to acceleration. The more resistant you are to acceleration, the harder it is to get you moving, the more inertia and the more mass you have. So that was an example of linear acceleration in a straight line. But let's look at rotational acceleration and how mass affects an object's ability to resist that sort of acceleration. So I've set up this small experiment where we have a bar on a pivot point, and there are two masses placed on each of the bars. And overall, the bars have the same mass. It's the bar plus two of these masses in each case. But something that is slightly different is the way that the mass is arranged. In one situation, the mass is very far away from the pivot point. In the other situation, the mass is very close to the pivot point. But overall, the total amount of mass is the same. So let's try and spin these bars. Let's see what happens when we try to accelerate these bars with a net torque. So as shown in this graphic, the bar with the masses that are far away from the pivot point is more resistant to angular acceleration. It is harder to accelerate, it's just a little more sluggish, whereas the bar with the masses closer to the pivot point is less resistant to angular acceleration. It's actually a lot easier to accelerate. And just to show you the real life version, we experienced this in class with these two bars with the different masses, but the one with the masses on the end definitely spun a lot slower. You might have felt more resistance as you were pushing it, but the one with the masses on the inside definitely spun a lot easier when it was pushed on. So even though these bars have the same mass is clearly not enough to describe how these bars are going to react to the torques that we are placing on them. It's something more than just mass. We need another term to describe these systems. And what we are going to use is something called the moment of inertia of the object. And the variable that we use for moment of inertia is a capital I. But moment of inertia is the analog to regular mass for rotational motion. And it is the measure of an object's rotational inertia. And rotational inertia is an object's resistance to angular acceleration. So these two bars react so differently because they might have the same mass, but they have different moment of inertias. So they have different resistances to angular acceleration. They're going to react differently to these torques. So they have the same mass, so how is it that they have different moment of inertias? Well, the moment of inertia actually depends on three things about an object or a system. The first one is still the mass of the object. The mass does matter, but there's two more things that matter. The second thing is the way that the mass is distributed throughout the object, and the third thing is where the pivot point of the object is. These three things combined will allow us to define the moment of inertia of a rotating object. In the next video, we will go over these three things in a little bit more detail, but for now, the biggest things you need to know is that objects not only are resistant to linear acceleration, but they are also resistant to angular acceleration. The property of the object that tells us how resistant an object is to linear acceleration is going to be inertia or mass. But the property that tells us how resistant they are to angular acceleration is going to be rotational inertia or moment of inertia.